Welcome to an example on how to use Green's theorem to evaluate a given line integral. Here we want to evaluate the line integral along the curve C, where the curve C is a rectangle with vertices 0, 0, 2, 0, 2, 4, and 0, 4. Let's begin by reviewing Green's theorem. Green's theorem states that if we let C be a simply connected, piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R, so if the curve C has a positive or counterclockwise orientation, the region R is always going to be to the left of the curve, and we let the vector field F have components P, Q, where P and Q have continuous first-order partial derivatives, then the line integral along the curve C of f dot differential R, or the line integral in differential form, is equal to the double integral over the region R of the partial of q with respect to x minus the partial of p with respect to y differential a, where again q is the y component of f and p is the x component of f. When the path of integration satisfies Green's theorem, we denote the line integral as shown here, where we have this circle in the middle of the integral symbol, which in our example we had. And before we go back to our example though, let's talk more about what a simply connected piecewise smooth curve with a positive or counterclockwise orientation is. And let's first talk about a simply connected curve. Here are two examples of simply connected curves that enclose the region R. And notice how both of these also have a positive or counterclockwise orientation. And here are two examples of curves that are not simply connected. And in some special cases, Green's theorem can still be applied if the curve is not simply connected, for example in this case here, which we'll talk about later. But the specific wording of Green's theorem states that the curve C must be a simply connected, piecewise smooth curve with a positive orientation, and here are three examples. Each of these curves are simply connected, piecewise smooth, and have a positive orientation. Notice how in this example, the curve C is made up of four pieces, which make it piecewise smooth, and we can also see it's connected and encloses the region R. Here the curve C is made up of three curves to make it piecewise smooth, and again we can see it's connected and encloses the region R. And this third example is similar to the second example. And notice in each case, the curves have a positive or counterclockwise orientation, which is indicated by the arrows along the curve. Going back to our example now, again we are told because of this circle here in the integral symbol that the curve C does satisfy Green's theorem, but just to show this, if we were to plot these points in the Cartesian plane as we see here and form the rectangle, the orientation would be in this direction here, a positive orientation or counterclockwise orientation, and notice how the region R is always on the left side of the curve. So beginning with the given line integral, we have the line integral along the curve C, where the curve C does satisfy Green's theorem of x y squared dx plus x to the fifth dy. So this tells us that P is equal to xy squared and Q is equal to x to the fifth. So now let's find the partial of Q with respect to x and the partial of P with respect to y. So the partial of Q with respect to x is equal to the derivative of x to the fifth with respect to x, which would be 5x to the fourth. And the partial of P with respect to y is equal to the derivative of xy squared with respect to y, which would be 2xy. So now applying Green's theorem, this line integral is equal to the double integral over the region R of the partial of Q with respect to x, which is 5x to the fourth, minus the partial of P with respect to y, which is 2xy. And then for differential a, we can use dx dy or dy dx. Because the region R is a rectangle, it really doesn't matter. Let's first integrate with respect to x, then with respect to y. And now we'll determine the limits of integration, first with respect to x. The region R is bounded to the left by x equals 0, and to the right by x equals 2. So limits of integration with respect to x are from 0 to 2. And the region R is bounded below by y equals 0 and above by y equals 4. So limits of integration for y are from 0 to 4. And now we integrate with respect to x first. So the antiderivative would be 5 times x to the fifth divided by 5 minus 2y times x squared divided by 2. Let's go ahead and simplify the antiderivative. So we'd have x to the fifth minus x squared y. Now we perform substitution for x to find big F of b minus big F of a. So when x is 2, we'd have 2 to the fifth minus 2 squared times y minus, notice both terms contain at least one factor of x, so we'd have 0 minus 0. Simplifying, we have the integral from 0 to 4 of 32 minus 4y, differential y. Continuing on the next slide, integrating with respect to y, we'd have an antiderivative of 32y minus 4 times y squared divided by 2, which would be minus 2y squared. So big F of b minus big F of a is going to be 32 times 4 minus 2 times 4 squared minus, when y is 0, both terms are 0. So here we have 128 minus 32, which equals 96. So because the given line integral satisfied the conditions of Green's theorem, we were able to evaluate the line integral by writing it as a double integral and then evaluating. I hope you found this helpful.